Howdy Huskies, welcome. We are going to do our intro to 6.4. We're going to start 6.4. This is 6.4 regular. Switching it up on you. If you look down here, I'm going to move this over so you can see. It is 9:20 p.m. Getting cray-cray. A little bit different here. So you know my videos are long enough, so we're going to skip the review questions. They're important, don't get me wrong, but we're going to jump right into graphing our polar equations today. We're going to start with circles and lines, and then we're going to add two new ones. So we have cardioids and limacons. Limacons being French. So ladies and gentlemen, let's start with the stuff we know. So we're going to start with lines. Now lines are going to be special because they're going to be the only one with its theta is equal to an angle. So it's the only one. The rest of them are going to use r, and we'll get to that in just a second. So because it's r equals an angle, remember it's going to be a straight line. It's going to be at that radian measure. Okay. Sometimes it's degrees, but the ones we're going to be looking at today specifically are in radian measure. So I'm going to go a little bit out of order today. So let's go ahead and jump all the way down here to number 4 and do this one. So these right here on number 4 is going to be a line, or lines, because we have two of them. So our first one, notice that is a positive pi over 6. So that's going to be right there. So we're going to say that no matter what our radius is, our theta is always pi over 6. So our radius could be 1, 2, 3, 4, 5, 6, or it could go in the negative direction. Okay, that's okay too. But regardless of what that radian measure that we have, it is always, boom, pi over 6. So that's going to be our first one. Now the next one here, notice it's a negative. So I agree, 2 pi over 3 is chilling right here. But since that's a negative, we're not going to use this one. We're going to go in the negative direction, which means you're going to cruise all the way over here. Oh, I passed it. All the way over here to pi over 4. So this is going to be negative 2 pi over 3. So again, regardless of what that radian measure is, it's always going to be negative 2 pi over 3. So if we connect the dots there, it's going to look like this line right here. Cool? So those are our two lines. Again, the big giveaway is it's theta, boom. So if you see that theta, think lines right off the bat, because that's going to be our dead giveaway. The rest of them, we're going to get a little creative because they're either going to be circles, cardioids, or limacons. So let's go ahead and start with the one we feel the most comfortable with. And that's going to go ahead and be circles. So as we learned in geometry, this is a circle. The idea is that we have a center, and then we have some sort of radius, and then we have a nice little diameter. This is wonderful. Cool. But what we're really going to be looking today is the equations of these in our polar coordinates. So let's start with the first one. So the first one is going to be r equals m. We've encountered this in previous videos. So m is going to be our radius. So the idea is if we had r is equal to plus or minus 6, that means our radius is going to be 6 and going in every direction. If it's going to be radius is equal to plus or minus 3, our radius is 3 regardless of the direction we go in our circle. So let's go ahead and jump down here to number 3, where we see, in fact, our radius is 6. So if I go in this direction, 1, 2, 3, 4, 5, 6, or down 1, 2, 3, 4, 5, 6, or even at an angle, 1, 2, 3, 4, 5, 6, it is always going to be 6. So that is our graph there. So we really, really like this one. So when it's just a number, you're thinking circles, because that's what our radius is at all times. We love that one. But we're going to spend the majority of today is when it looks in this form right here, which we see is, well, that's not my highlighter. Let me highlight this right here. So it's going to be d sine theta and d cosine theta, where d is the diameter of our circle and it's tangent to the pole. So what that means is tangent means it's going to touch exactly once. So the idea is if this is my pole right here, it's going to hit it exactly one time. Okay, it could be going right there. It could be up and down, as we'll see. Obviously, these circles aren't going to intersect, but you can see that they are tangential or hitting just once. So let's go ahead and jump in with that. So whenever we are looking at thetas, and since we need to make sure that we're trying to use the work smart or working smarter, not harder, we're going to look at our principal values. So it's been a while. So let's go ahead and look at our principal. Oh my goodness. Values. Sorry, I'm probably pretty spelled that wrong, but you know, math teacher, not an English teacher. So our principal values, remember when we are in our principal values for our cosine, remember we're going to go ahead and be in specific regions. So I'm going to flip to the next part of my notes here to make sure that we are good. So that is going to go ahead and be in our first quadrant and our second quadrant. Okay, if we were to go ahead and set it up for cosine, it would be these two right here. Because remember, it goes all students. So we're going to use our principal values. So notice I have those principal values right here. So I know that this takes up a lot of room. So hit pause and write down this lovely little chart here, because that's what we're going to be using to go ahead and graph the circle on our lovely polar grid here. All right, welcome back. So the idea is if we have, and we're just going to look at just specifically this one right here, how does that make our circle? So what we're going to do is we're going to put in values for theta. So that's why we're going to use just our principal values here. So let's go ahead and jump right in. So if I have 4 cosine of 0, we know what this, hopefully using our unit circle, is going to be. This is going to be 4 times 1, which is 4. Okay. And so if I were you, I would use different colors. It's going to make this really a little bit more evident. But in this first one, we're going to go 0, 4. So here obviously is 0, and then I'm going to count to 1, 2, 3, 4. This is going to be that point. I'm going to switch colors here to our next one. So 4 cosine pi over 6. And pi over 6 is going to be root 3 over 2. And we can multiply that across to get 2 root 3. But really, we're just going to end up with the decimal 3.46. So at pi over 6 here, I'm going to go 1, 2, 3, and a little bit extra. I'm doing the dots, so obviously we don't do these yellow dots that we see or these blue dots right here. I'm just doing that to see how you can see how I'm moving. So there's going to be 4 cosine pi over 4. Notice I told you this was going to be a video. We have lots of values to do. So 4 times root 2 over 2. And when you multiply, that's going to give us 2 root 2. But really, it's just the decimal 2.83. So here at pi over 4, we're going to go 1, 2, and a little extra here. It is an approximation because we are using a calculator and a rounding. So 4 cosine pi over 3. So that's 4 times 1/2, and that's going to be 2. Well, thankfully, we have a number finally that we know that's going to be pretty easy peasy lemon squeezy. Alrighty, and then we are going to have 4 cosine pi over 2. Ooh, we're lucky again. So this is 4 times 0, which is going to be 0. So notice if I go ahead and I'm going to use my rainbow pen here, woo, we have this lovely little half circle so far. Let's continue to see what we're going to get. Okay. Now, as we go ahead and we notice we're going to go into this quadrant over here, that's when our cosine is going to be negative. So when we put in these values, check out what happens. So 4, that's not my, one of my blue pen, not my blue highlighter. So 4 cosine 2 pi over 3. And if we put 2 pi over 3 on our unit circle, we realize that that's a negative 1/2 for cosine. So this is going to be a negative 2. So here we are chilling at 2 pi over 3. And 2 would be 1, 2 right here, but that's not where it is. So I'm going to erase that. I'm going to go in the negative direction. So we're going to go ahead and go 1, 2. Boom, right there. Lovely, wonderful. So then we'll go ahead and do another one. I'm starting to run out of colors. That's a bad sign, right? Alrighty, we'll go ahead and do this one again. So we have 4 cosine 3 pi over 4. So that's going to be 4 times negative root 2 over 2. And that's going to be negative 2.38. So here we are at 3 pi over 4. We're going to go in the negative region. So 1, 2, and a little extra. And we're starting to see something, as I mentioned, when we connected these dots right here, we are going to start seeing that we have some similarity down here, and that's completely on purpose. So let's finish this out so we can see that. So it's going to be 4 cosine 5 pi over 6, and that's going to be 4 times root 3 over 2. That is negative, so negative 3.46. Again, notice the positive and the negative version. And then 2 pi, so 4 cosine of 2 pi, excuse me. This should be just pi. Shouldn't do stuff at too late at night, so thankfully we caught that mistake before we went too far. So pi is going to be 4 times negative 1, which is negative 4. So normally I would go here, I'd go 1, 1, 2, 3, 4, but it's not going to be that because it's the negative direction. So look, I ended up right back where I started. Okay, so if I were to connect all these dots, my friends, notice that I get a circle, not the most perfect circle because I'm not an artist nor an English teacher, but you can see where that happens. Cool. So notice we said that this D was our diameter. Our diameter is 4. And if we look, we can count 1, 2, 3, 4. So that holds true. And if I go up and down, that would be consistent in any sort of which way. So that's awesome. So let's compare now what would happen if I made it a negative. Well, then all these would just be a sign change. So then I'm going to go ahead and erase this over here. I'll go 1, 2, 3, 4. I would have it in this direction, but it would look like the exact same graph, as we could see, because the negative would just change our signs. Alrighty. So I want us to take a look at this because this is going to come back in to be pretty important here a second. So if it's cosine, it was on the right here. If it was negative cosine, it was on the left here. That's going to be a trend that we're going to want to keep on our eye on. Alrighty, so we're going to do the same thing over here. And so let's go ahead and fill this in. So you can probably start doing this right off the bat. You can be like, all right, I know what well, before we get too ahead of ourselves, remember that if it's sine, our principal values are all students teach calculus, or all students take calculus. It's going to be in these two right hands. So that's why we're not using the exact same values. We're going to go from pi over 2 to positive pi over 2. That is going to be our principal values for sine. Okay, so notice we have principal values. We should write this down. Principal, lordy, my spelling's getting worse. Values, in this case, is going to be the quadrants 1 and 4. Cool? Alrighty. So we're going to just go ahead and plug these values in right here and see what happens. So we get 5 times the sine of pi over 2. And so that's going to go ahead and give me 5 times 1, which is just 5. So that means that pi over 2, I'm at 1, 2, 3, 4, 5. That's interesting because before it was on this, we'll call it the polar axis, side to side. Well, now it's going up and down. It's the old y-axis if we were on a rectangular grid. So this one looks like it's already starting to go in a different direction. So let's go ahead and continue to investigate here. So if we need to go a little bit faster, this is going to go 5 sine pi over 3, which is 4.33. I'm just going to go ahead and do all these right at once because you guys can get the gist at this point. You're just plugging these in a calculator because you have root 2 over 2. You have root 3 over 2, those values are not going to be helpful here. So that's why we're just going to go and plug them into a calculator. And I'm just going to shimmy on down to fill out our values here. And then we're going to have 5 sine of 0. That's going to be 0. Messing with my color schema here. So notice I'm going down to 11 pi over 6 down here. Okay, so 5 sine 11 pi over 6. And remember, in this quadrant down here, the fourth quadrant, our sign is negative. So this would be 5 times a negative 1/2. So that's a negative 2.5. So we're going to see now that we're in the negatives. So this is going to be 5 sine 7 pi over 4, which is going to be negative 3.54. 5 sine 5 pi over 3. Just plugging this in the calculator, negative 4.33. And then last but not least, 5 sine 3 pi over 2, which is going to give me negative 5. All right, so we have our points again. Let's investigate. So if I go ahead and I do this one right here, so at pi over 3, I'm at 1, 2, 3, 4, and a little extra. I'll erase those dots right there. I just want to, I do those little dribbles there just so you can see how I'm moving here from my pole. So it's going to go 1, 2, 3, a little extra. Erase my dots here. This one, pi over 6, is going to be 2.5, so 1, 2, little extra. Here at 0, boom. And then, of course, here we're getting into the negative, so 11 pi over 6. You would think that I'd be moving this way where my dots are going because I'm head that way, but because I have a negative right here, I have to go in that opposite direction. So it's going to go ahead and go 1, 2.5. Alrighty. Then we're going to keep on rolling, so negative 3.54. 1, 2, 3.54. And then right here on this one is negative 4 point and a little extra. So 1, 2, 3, 4, and a little extra. And we can see here our circle, boom, is on top. Okay, so if that is what our sign is, our sign kind of goes up. What do you think that's going to happen to our negative 5? Think about it. Let's refer back. So notice that these, they kind of went in different directions. So it makes sense that sign, because it's the y, would be in direction going down here. Cool? Again, an important concept. So let's kind of summarize this up. But I do want to go ahead and just make some observations real quick. If I look at these decimals here, I'm going to highlight these ones. Boom, 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 boom. Those are nasty decimals, and that's going to make our lives a little bit tougher. And since at some point we are going to have, ladies and gents, a calcular portion and a non-calculated portion, it'd be beneficial to use values that we know. Like, we know this one is 1, nice and easy. Any of the root 3 over 2s or root 2 over 2, stay away. But I know a 1/2, I know a 0, a negative 1/2, and a 1. Those values are going to be super easy. So we're going to come back to that in just a second. Same thing over here. So saucy decimal, not too bad with the 2.5. Saucy decimal, let's stay away from those. So we're going to use these ones right here for sign, because even though we are going to get some decimals, at least they're not horrid. So, ladies and gentlemen, boys and girls, all these so far we can do in our calculator. It is important to note that how. So let's go ahead and take a look at some ideas for a calculator before we move on, since we're here. The first thing we're going to have to do is going to have to say mode and go to polar. Okay, so I got my calculator up here. Notice I have the mode button. If I go down, make sure radian is highlighted, and then go down where it's function, and then go over and hit enter on pole. So if you hit enter on pole, that's going to become highlighted, and then when you hit the y equals, so now that we have that, if you go y equals, you're going to see that it says r equals. So y equals is now r equals. Well, that's fancy. So if we look at 4, and then if we hit cosine, notice this right next to our alpha, our x button, has a theta. That's now our input value, as we showed with our other ones. And we hit graph, boom shakalaka, there we go. That's kind of cool. There's some other cool zooms that you want to take a look at. So if you hit the zoom button, Z standard is always going to go to that box that we love, but Z trig is going to be helpful because it's going to kind of put things in terms of, hey, I know this. This goes 1, 2, 3. It sort of helps us see things in trig functions a little bit easier. So I try to do Z standard for the most of my time, but you can see that we did that one right. If we were to go ahead and clear this out, let's do the -5 sine theta to prove our hypothesis that this goes down because it's negative. Hit the graph button, boom shakalaka. So now you know how to do that. The only one that I'm not exactly sure how to do, I'm sure that someone knows at some point, but that's the one where your lines with the theta, since these are R's, I'm not exactly sure how to do that on the calculator, so hopefully another teacher could either let you know or clue us all in, because I don't know. So, ladies and gents, let's go ahead and go back to our notes and continue on talking about some symmetry. Alrighty. So let's fill in some of these blanks. So symmetry, just think of like a butterfly. Or, that was the worst butterfly ever. Yay! Alright, so with our butterfly, the idea is that our wings are symmetric. So what we have on one side should mirror the other. When we think of that function, we should think of a cosine function. A cosine function means that when you plug in a negative x, you get the same thing as just a regular x for cosine. We call this an even function. Therefore, the graph will have what we call polar axis symmetry. So to tie it on into what we just got done doing, the polar axis, we're going to notice that polar axis. I'm going to pull this right here. Polar axis, some would say that that is our x axis in rectangular mode, but it's our polar axis when we are in polar. So when we started to go ahead and draw our circle, what we noticed is that when we put in the values that were supposed to be negative, that it just moved us back down here to be symmetric. So this right here is our mirror image, okay? And that's why we got to move things around. So it is going to be symmetric in respect to the line theta is equal to 0, which again is that polar axis, okay? Now, we're going to use quadrants. Again, this has to do with our principal values, and the principal values are going to be 1 and 2. Alrighty? So those are going to be the values that we're going to use and we're going to plug into. And we kind of knew that right off the bat, as with the ones that we just got done doing anyways. But I'm going to go one step further. The ones that we know and that we really can use, and these are going to be what we want to star, because we're going to use these the most. So when we are indeed dealing with cosine, the ones we knew were 0, pi over 3, and then this was pi over 2, 2 pi over 3, and pi. These were the values on our that were not root 3 over 2. So root 3 over 2 is a decimal, that's rough stuff, and root 2 over 2, that's a decimal we don't know or we don't want to do. So we're going to live in 1/2 land, or 1 or 0. So that's why we went ahead and used this one and this one over here. So remember, cosine was side to side. If we look right back over here on this one, we notice that this was cosine, and then this was going to be, this was cosine over here, and this was negative cosine right there. Okay? So important to note, but that it goes over our symmetry, our line of symmetry of that polar axis. Okay? We sort of proved that. And then our sine, if I erase this one, notice we started with these guys right here, and then we noticed that it was symmetric on that side, so our axis of symmetry here for these is going to go right up and down. It doesn't have necessarily a fancy name, so we're just going to call it the line where theta is equal to pi over 2. And this is what's known as odd symmetry, because if you have sine of negative x, that gives you a negative sign. Okay, so when we did this again in the previous example, just to show us what's going down, we started with this side, and then we got the mirror image. Let me try that with the colors that we used previously, and we got that. So we are going to go ahead and be, for this one, in our quadrants because of our principal values of 1 and 4. Okay, and the values we're going to use are going to be the ones when we know are going to be 1/2. So 0, pi over 3, and then this is going to be pi over 2, and then 3 pi over 2, and 11 pi over 6. Cool? Alrighty. So, ladies and gentlemen, boys and girls, welcome to our new graph. And it's been a while since we've actually introduced a truly new graph, but cardioids is going to be a new graph. So, to put this kind of in some context here, the idea is that cardioid kind of comes from cardiac. Cardiac we know is obviously kind of like a heart, and so this is kind of like a heart graph in very basic terms. But the idea is it kind of gives you the much more curved pieces. Okay, so we're going to call this part right here the tip, and it's going to be pointing away from our pole. So for cardioids, we're going to have our pole where we're going to have our little parts of our top parts of our heart, and then the tip is going to go the farthest away. Cool. So welcome to this welcome to this new graph. It is pretty common. Again, you can see that we're going to use this again, but if you have and not an artist here, this looks like an ice cream cone, but it's supposed to be a microphone. And if you go ahead and you look at this, if you look at how it sort of brings in different waves, it brings in different waves in different decibels, I should say. And so each one of these different cardioids has a different decibel reading that will amp up or take down the volume to a microphone. So that's your fun fact of the day. And if you guys like using mics or in a band, you are going to be using that graph in your future. Well, hopefully, that'd be pretty cool anyways. Let's look at the graph. All right. So the first thing I want to point out is obviously we're going to have cosine here and sine here, and that's going to be very important, okay? But these m's, okay, are going to be pretty important, okay? And I want you to note that these are going to be the same values, because when they're different values, it's going to be a different graph. So notice I have 2 and 2, 3 and 3. So those are going to be the same values. And when those are the same values, my friends, that is going to go ahead and give us our chordioid. So let's go ahead and get us started. So we're going to start off with making another table. So if I go ahead and take a look, I am indeed in cosine land. So since I am in cosine land, we're going to go ahead and be in quadrants 1 and 2. So the values that I need for cosine, so 1 and 2, I'm going to use my cosine. And I know that right here at pi over 3, that's going to be 1/2. So that's why I use the pi over 3 and the 2 pi over 3. Alrighty, so we're going to do the exact same strategy we just got done doing and put this into 2 minus 2 cosine theta. So 2 minus 2 cosine of 0. So we obviously know that the cosine of 0 is going to be 1. So 2 minus 2 times 1 is going to go ahead and give us 0. So I have 0, 0. That's my first point. And I'm going to use a bunch of different colors again. If you would like to do so, please feel free to do so. So I'm going to go 2 minus 2 cosine of pi over 3. Now we know that pi over 3 is going to be 1/2. So 2 minus 2 times 1/2 is going to be 2 minus 1, which is going to be 1. So we're going to go ahead and go to, remember, we plugged in this pi over 3. So that's why we're going to go to just 1, which is right there. Alrighty. So we're going to go 2 minus 2 cosine of pi over 2. So 2 minus 2 times 0 is going to go ahead and give me 2 minus 0, which is 2. So right here at pi over 2, I'm going to go 1, 2. Hopefully these, you're picking up how we're plotting these, going with our theta and then our radius. All right, so 2 minus 2 cosine 2 pi over 3, lots of unit circle review stuff. So this is 2 minus 2 times a negative 1/2. Why is it negative? We're in this quadrant. Remember, it goes all students. So when that's circled S, remember that means our cosine is negative. So this is why that's a negative 1/2 right there, and I'm not just being goofy. A negative times a negative is going to make this a positive, so 2 plus 1 is going to give me 3. So we'll go ahead and go 1, 2, 3. And then last but not least, we're going to go ahead and go with pi. So 2 minus 2 cosine at pi, so 2 minus 2 times negative 1, which is going to become 2 plus 2, because a negative and a negative make a positive. So this is going to be 4. So 1, 2, 3, 4. Alrighty. So notice it kind of looks like a heart that way. And, well, didn't we just get done talking about some symmetry here? So cosine has got symmetry over our polar axis. So that means that that's going to be the same values in reference to the other side. So here at pi over 3, we would go ahead and say, alrighty, let's go ahead and do that at 5 pi over 3. So we'll go ahead and say, all right, pi over 3 and 5 over pi over 3 is at 1. So there's my 1 right there. And then I'm going to go ahead and go over to here. So here at pi over 2, I was at 2. So I'm going to go to negative 2. Because again, they're going to be symmetric. So the distance between my line of symmetry has to be the same, has to be congruent. And then here was 3. So if I look at 4 pi, this is going to be 1, 2, 3. And then obviously going to hit back there. So you can see kind of here how it is a beautiful heart. Notice that my tip is going to be over here and my pole is going to be right here. It's sitting on the pole and the tip is going away from it. Cool? Alrighty. If you feel so inclined, I kind of set up this table so far. Why don't you hit the pause button and give it a shot, see how well you do, and then come on back. Alrighty. So one thing that might be helpful is that you do have your polar graph here. So with sine, we know that we're going to use pi over 2, pi over 6, 0, 11 pi over 6, and then 3 pi over 2. Sometimes it's helpful to circle those so then you know exactly which ones you're going to go ahead and use. And it also kind of shows which ones are going to go on the other side. So this is going to be 3 plus, because it's 3 plus 3. So 3 plus 3 sine theta. So 3 plus 3 sine pi over 2. So at pi over 2, that's going to be 1. So 3 plus 3 over 1 is going to go ahead and give us 6. So 1, 2, 3, 4, 5, 6, all the way there at the top. Alrighty, so let's go ahead, and you guys probably get the gist from here on out. So sine pi over 6. So that's going to be 3 plus 3 times 1/2, which is going to be 4.5. See, some decimals are unavoidable, but at least they're decent. So again, the nice reason, if it's circled, it makes it easier to find. So 1, 2, 3, 4.5 there. So 3 plus 3 sine 0. So the sine of 0 is going to be 0. So 3 plus 0 is going to be 3. So 0, 1, 2, 3. There we go. And then we'll go to our next one here. So 3 plus 3 sine 11 pi over 6. So 3 plus 3 times a negative 1/2. So why is it negative? Let's double check. All students take calculus. We're in these two quadrants, and now we're into specifically this one. That is where cosine is positive, and since this is sine, that's why it comes out to a negative. So this is going to be negative 1.5. So, sorry, not a negative 1.5, excuse me. This is a negative, but 3 plus 1/2 is still going to be a positive. I was like, that shouldn't go that way, but thankfully we caught this, so 1.5 is right there. And last but not least, we're going to get 3 plus 3 sine of 3 pi over 2. So there's going to be 3 plus a negative, 3 times a negative 1, which is 0. Boom. So, ladies and gentlemen, boys and girls, we can see, if I draw this correctly, there is half of my heart, half of my cardioid, and so the idea is to find the other half. Should look something like that, right? So it should be symmetric. So here on this 5 pi over 6, it should be 1, 2, 3, 4.5. 1, 2, 3. Let's see, 1, 2, 3, 4.5. So it should be right there. I was a little off, but you guys can get the gist. Then 0, 3 would have been 1, 2, 3. That one's a little bit better. And this would be 1.5. Boom, shakalaka. There you go. Okay. So you can kind of see how these are set up. And if you use the values of one of these key values for cosine and sine, not too shabby. So let's try to make this easier and notice some trends, okay? So first off, if it's cosine, it's either going to be this way for circles, or your hearts are going to go the other way, or cardioids. So the idea is that if it's cosine and a positive sign, so a positive sign in between. So remember, if we look at our equation here, there it is. It's plus or minus. So if this is a plus right there, a plus in between, then the tip is going to go to the right, always. And if it's negative, it's going to go to the left. So right, left. So from here on out, you should be able to look at this and go, okay, it's negative, boom, that way. Oh, it's cosine and positive, boom, it's going that way. Okay, so signs were up and down. So if it's positive, that's going to be up. And if it's negative, it's going to be pointing down. Easy peasy lemon squeezy. All right, so ladies and gentlemen, as we go on to our next one, we are actually going to do the Limacons. So notice that with our Limacons now, though, is that we're going to have different graphs, and these, they're going to look a little bit different because those values aren't going to match. So if we take a look at these, those matched and matched, 3 and 3, 2 and 2. These are going to be different values. We're going to have K and M. Okay, so Limacon is going to be a couple of different graphs. So we're going to have what we're calling a loop or not to loop. So loop or not to loop, that is the question. I had to go there, right? All right, so if it's a loop, the idea is it kind of looks like a cardioid, except in the middle, we're going to have a little loop. So if it's going to be no loop, we're going to call that a dimple. Then it's still going to look kind of like a cardioid, but it's not going to have such a pronounced little heart that dips in, and there's nothing here. Now, what's going to be important is that right here on a loop, that intersection where it doubles over onto itself, that's going to happen at a pole. At a dimple, the pole is going to be inside, and we're going to come to that, back to that in a little bit. All right. So, ladies and gentlemen, the idea is these Limacons are going to be all about what's going on with the K and the M. So if we take a look, if your K is less than, okay, that means that your loop is going to occur. Okay, so that's going to be something we're going to want to make sure that we take a look at and be good to go. So that's what these next set of examples are actually going to be all about, is there a loop or not? And I'm going to add a new extra wrinkle. So for this one, we'll label this A, B, C, D here. What I want to know is, step one, is it going to be a loop or is it going to be a dimple? So that's going to be the first question we are going to ask ourselves so we know basically what the graph should look like. The second thing I want us to know is, where is the tip pointing? Okay, so where's the tip of my heart going to go ahead and take a look at? So with number one, if we take a look at this, this is going to be my K and this is going to be an M. A loop occurs when a K is less than M. So we are going to have a loop in this case, okay, because my trig function is bigger. So what direction is this going to be pointing for my tip? So it is a positive cosine, so the tip is going to be pointing to the right. And it's all about your trig function. So cosine is left or right, and positive is going to go to the right. All right, let's look at B here. So I'm going to put a 1 in front of here. So here, my K is greater than M. So we're going to go ahead and say that this is no loop. So this would be a dimple. So there would be no loop. So none of this, as we see here in blue. Okay, the pole is going to be inside. And so what is this going to be? Well, let's take a look. So sine is going to be up and down. And since it's a minus, that means that the tip of my heart here, of my limacon, is going to be pointing down. Alrighty. So, ladies and gentlemen, why don't you try C and D? Hit pause, give it a shot, come on back. So on C, we have a dimple, okay? And because we have a 9 that's bigger than our trig, and this is going to be going to the left, because it's a negative cosine. And then right here, this one's going to be a loop because my trig is bigger, and it's going to be going down because it's a negative sign. Easy enough? So again, that's some stuff that you should be able to read for your science, your circles, your limacons, and your cardioids is which way is it going? Sorry. Cardioids is which way is it going? Cardioids are like pants. That'd be legit. All right. So, ladies and gentlemen, what we're going to do is I first want you to go ahead and take this and apply it right here. So hold off on this one because we're going to change this one in just a second. So I have r is equal to 2, and then I'm going to put a 1 in there because it's an assumed 1. And so I'm going to say, alrighty, the first thing I'm going to go ahead and notice is that this is a dimple because my constant here is larger. Okay. I'm also going to notice that this is a plus sign, so my tip is going to be going up. So it's kind of like if I were to draw this just very basically, it would kind of be something like this. Okay. So we can see it's a positive sign, so it's going to be going up. We're going to have our pole inside. It's not exactly going to sit right there. And we're going to go ahead and go to tan. So we have the same points that we've been using, of course, for sine, because we know what the pi over 6 is. We know that's 1/2. So we're going to plug this into 2 minus 1 sine theta and basically do the same trend that we've been doing. So hopefully you're starting to pick this up. So, and notice I started at 3 pi over 2 here, but it doesn't really matter where you start, but I'm going to use those values. So minus 1 sine of 3 pi over 2. And so this is going to go ahead and give me 1. And then we'll go ahead and move on to our next one of 2. Excuse me, this is a plus. I was looking at my notes going, something was funky. There we go. So 2 plus 1 sine of pi over 6. And that's going to give me 1.5. And then 2 plus 1 sine of 0. That's going to give me 2. And then 2 plus 1 sine of pi over 6 is going to give me 2.5. And then this is going to give me 2 plus 1 sine of 3 pi over 2. And that's going to give me 3. All right, so let's go ahead and plot these. So if I start here at this first one, remember it goes theta, then my radius, so I'm not there. Notice my pole is this pink dot right there. I am not hitting my pole. My dimple should go around it, okay? So the next one would be pi over 6 and 1.5. So, oh, I went in a fun order, didn't I? I think that was supposed to be 11 pi over 6. There we go. So then this is 1.5. There we go. And then 0, 2. 0, 2. Boom. And then, oh, see, I put these in the wrong spot. That's why. So this, according to my math, should be pi over 6. And this will be 2.5. Apologize here, but the good news is that we're going to be on it. So 2.5, and then the last one here is going to be at 3. 1, 2, 3. So you can see how it's starting to look kind of like a heart with my little dimple, and then symmetric on the other side. So we'll go ahead and go to 1.5. That should be right here. And then we'll go fill in our dots here. There we go. Okay. Notice our pole is right here in the center and it's pointing up. So my tip of my limacon is on the top there. Okay. All right. Thank you for sticking with me. I know this is a lot. We'll get through this one as quick as we can. So I told you to hold off because we know that as this is no loop. So let's take one that looks for a loop for a spin. So we're going to actually cross this out and make this r is equal to 2 minus 3 cosine theta. So that way, ladies and gentlemen, boys and girls, we can actually see what a loop is. So in this one, we're going to tackle that loop. Okay. So if we look at it, we're going to go 0, pi over 3, pi over 2, and then pi. Oh, I'm missing one there. There we go. Alrighty. So the idea is that you guys at this point realize that you're going to plug this into 2 minus 3 cosine theta. And as you've been watching this video for long enough, I'm going to go ahead and hopefully just plug in my numbers correctly here. So this is -1, and this would be 1/2 or 0.5, and then pi over 2 is going to be 2, 3.5, and then this is going to be 4. All right, so those are my points. Let's make sure that this works. So again, it's a negative cosine. So negative cosine theta means it should point that way. Let's see if our values actually show this. So 0, -1 would be right there, and then 1/2. We're going to be right there, and then pi over 2. Whoops, -1. I put that at +1. -1 would be right there. So that's why I wanted to zoom in right there. Then we're going to have 0.5 right there. Then we'll go ahead and go to 2. So notice I have a -1. That's why I did this point right here at -1. Okay. And then 2 was this point right here, as we can see the 2 right there. And then 3.5. So 1, 2, 3.5. And then notice pi is 4. So 1, 2, 3, 4. So notice that this dips in. If I go ahead and highlight this yellow point, this is going to be where my loop is. So, and remember, it's going to intersect at that pole. So that's poles where things are going to cross out. So I have a loop right there, and then it's going to continue on like that, and then mimic on the other side. Cool. All right. So ladies and gentlemen, that is it. So if I were to sum this up, okay, and this is a long video, okay, make sure you're good on your trig functions. Look at all those colors. But cosine is side to side, as we can see. Sine is up and down, okay? So a cardioid, excuse me, is when these two values are the same. And then a Limacon is when they're different values, okay? All right, so I'm going to show you something cool on the next page. You don't have to watch it. It's just kind of cool. So if you feel like you want to little dive into something extra, but this has already been 50 minutes, so I'm going to get yelled at for it being so long. So I'm going to hit pause. If you're done, you're done. If you want to come back, come back. We're sticking around. So this first part you probably are all good with, okay? Circles, if it's a negative cosine, positive sign, negative sign, that's how your circles should look. I know these are not great circles, but this is our equation, and then D is going to be, I should say A, as I've written in all here, is going to be the absolute value of your diameter. Okay, so the negative just sort of tells you which direction you're going to go in, but then it should be basically whatever's going on from here on out. So if you can remember this part, it really is, hey, go to your pole, because all these are tangent to the pole, and then if you know which direction your A is, you can count up A, or down A, right A, or left A, and you can have a really good idea of what your graph should look like without actually having to put in your tangent or all your functions. All right. Moving on to the next one. With the next shape, we kind of summed it up with here with the idea that your cardioid is going to be some sort of almost heart-looking figure. So if it's cosine, remember, it's going to go either left or right. Sine is going to be up or down. So if it's a plus sign, notice the tip is pointing to the right. If it's a negative, notice the tip is going to be on the left. So left, right. And then this is going to be up and then down. So we probably knew that right off the bat. Remember that these two values have to match. It's either sine or cosine, just like up here it's sine or cosine. But here's the kind of the cool thing, is that this is a way to graph this or make sure that you did this correctly without actually even doing it and putting it in your calculator. So this point right here, where it sort of dips in, is always going to be at the pole. Okay, so we know that that's going to be at 0, 0. We know the tip direction based on what's going on. So if you know what the pole and the tip direction is, you already know what 2 points are on there. So it'd be nice if I could find 2 more. So what is that value? So from here to here is going to be whatever your M value is, and the same thing down here. So if it's a 3, as we'll see in our example, then be 1, 2, 3. So you now know what those values are right off the bat, and they are going to be on this theta over 2. And then how do you find where to put this tip point? Because now you know the tip direction, that from your pole to the tip is going to be 2m. So from here to here is 2m. And then it should be the absolute value of these. So if they're negative, we realize that those are all values that we can understand. So if this was 3 up and down, then this would be 1, 2, 3, 4, 5, 6. So let's take a look. So here we have 3 plus 3 cosine. So it's a plus cosine, meaning I know that the tip is going to be on the right. Okay, so I start here with the pole. Now my M, again, is this value right here is 3. So I go up 1, 2, 3. That's 1 point. Down 1, 2, 3. That's another point. And then the 2M is from the pole to the tip of our cardioid. So 2 times 3 would give me 6. So 1, 2, 3, 4, 5, 6. So then you can just go ahead and make your cardioid look like that. And so that's a good way to double check to make sure that you did all the other math right. Now, the reason why we're showing this to you at the end, and this is optional, is because the other ways that we did it way back over here, or I should say here, is going to be really helpful for further going on. But this stuff right here is going to be a nice little trick to help you out. Cool? All right, pausing for our last one with our Limacon. And so my little helpful piece for Limacon is that we kind of know the idea if it's up, down, left, or right based on sine and cosine at this point. So let's really just focus on loop or dimple. So there is a little shortcut for our loop. That, remember, that's the trig piece is bigger. Our m is bigger. M is right next to the sine and cosine. That's why I say our trig is bigger. So what you're going to do is that you can go ahead and set this up and double check is that this right here is always going to be at the pole. Your loop, the distance of our loop is going to go ahead and be k minus m. And then the absolute value of that, whatever the bigger one is, minus a smaller one. But really it doesn't matter because the absolute values will do that. Okay. So then to find out what this point is and this point here, from here on out is pretty much the same thing as a cardioid, is that this would be your k value. And the k value, remember, is the one that's in front. Okay, so this is the number that's going to be in front. And then just like we did before, from here to here, so if this is our tip and this is our pole, from pole to tip, it's going to be the absolute value of k plus the absolute value of m. So you take whatever those absolute values of those number is and add them together. Okay, so we have a nice little shortcut for that one. Alrighty, so for our dimple, that means our constant is bigger. Remember that this is our pole. Okay, so it's still sort of like a cardioid in the fact that if I go up, this is still my k value, and this is still my k value. Okay, and just like we did with a cardioid, is pole to tip. So from the pole all the way over here, the idea is that we're going to go ahead and say it's k plus m. So just like we did from there, this would be the tip of our Limacon, and from the pole to that point, you're going to add them together. And then from here to here, this, from the dimple, is what we're going to call this spot right here. From the dimple to our pole at the center, you're going to go ahead and subtract them. So it's a value of k minus m. Cool. So let's go ahead and take a look at a quick example here. So this is the example we changed. So now we can actually see what's going on. So we can see that here our trig is bigger. And I had to change it because I was like, I just realized like that looks familiar because we just did it. So in this case, my friends, we can see that our constant is bigger. So if our constant is bigger, that's going to be a dimple. So that we know that because it's a negative cosine, it's going to be pointing to the left. So it's going to kind of look like that's the worst drawing ever. That's what happens when it's 10:30. It's going to look something like that, right? So our pole is going to be inside. So I like to put my pole right there, even though we're not going to use it. Okay, so this is my k. So I'm still going to go up 1, 2, 3, and down 1, 2, 3. So those are going to be 3 points right there on our graph. So then how do I find my dimple? So my dimple is going to be the absolute value of 3 minus 2. I just take this 3 and this 2, and so that's going to give me 1. The absolute value of 1 is going to be 1. So here, right here will be my dimple. And then to find what the tip of my Limacon is, I'm going to do 3 absolute value, 2 absolute value, or just take the numbers and add them together. And you're going to get 5. So 1, 2, 3, 4, 5. And so that's how it's going to look. So that is your shortcut to help you out with this. So I get that this video was an hour long, but the last 10 minutes you definitely didn't have to watch. So that was up to you. So ladies and gentlemen, boys and girls, I hopefully found this was easy. I know it was a tough, long video, but we did the best we could when you guys aren't in front of us. So take care. We'll see you next time.